Hello everyone, my name is Alan Cueva and today we're gonna talk about the short paper feature engineering versus feature selection versus hyperparameter optimization in the Spotify song popularity dataset. This work was made by Brendan Tierney and I. We are from the School of Computer Science of the Technological University Dublin. As I said, my name is Alan Cueva and I am a software developer with more than 10 years of experience in many companies like Oracle and MariaDB. Now I am a full-time student in the Technological University Dublin and my fields are data science and computer science. Nowadays, feature engineering research seems to be less important than other techniques. The general idea of this work is comparing three different techniques, which are feature engineering, feature selection, and hyperparameter optimization in the Spotify dataset and identify which one has a better improvement over the machine learning task. These techniques can and are implemented together, but we think it's important to identify which one is better and deserve more research and time. At the end, the results prove that the feature engineering has a much higher effect on model efficiency when compared to alternative approach. It is normal for an early stage or novice data scientist to get impressed by sophisticated machine learning techniques such as feature engineering, feature selection, and hyperparameterization. On the other hand, feature engineering is the implementation of typically handmade algorithms over the feature vector, and it's made by the data scientist using their domain knowledge. And this alternative is present in many machine learning competition winners, and for this reason it make us think, or it make a question ourselves what technique is better. A little bit of relate research. Some common research topics in machine learning literature are about comparing different methods for a specific task. For example, there is many medical research like cancer prediction and many other stuff, and other typical another topics is compare similar techniques to choose which one works better in what scenarios in order to use only one alternative. In this case, we compare similar techniques in order to choose one of them. And in feature engineering research, it is common to find comparison of different combination of engineered features and methods to identify a pattern. Like for example, in neural network, this kind of feature engineering is better, or for decision trees, this one is better. That kind of research. But if the real objective of machine learning task is to reduce the error, there is not reason to not compare different techniques. I mean, in this case, they have something similar in the case of comparing similar techniques, but there is no reason to not do it. Returning to this work, the first step is feature engineering. So the Spotify song popularity dataset consists in more than 129,000 rows and 17 variables, of which 3 are strings and cannot be used in the feature vector without any transformation. They only accept numerical values. So this step focuses in creation of new features from these string features. In order to validate the new features, a correlation test was executed over H1, and the results were classified from very weak to very strong using this criteria. Just as a note, all statistics generated for this work were statistical significant. So the new variables that we create, I'm gonna mention each one and do a brief description of it. First one is numerical release date. This is a numerical representation of the date, but at the end it was rejected because it is very similar to the year, another variable present in the dataset. Just it's mentioned as a comment, and because the relation with other variable was rejected. The next one is the number of artists. The artist is a string formatted in a Python array, so it can be many artists. And this is the quantity of artists of the song, and it presents a negative correlation, and it fits with a partner where songs with more than 3 artists tend to be unpopular. There are some songs with, I don't know, around 15 artists, and they are not too popular songs. Another one is the main artist popularity. This one was a challenge. The idea was to calculate the popularity of each artist and each artist of the song and get the mean of artists of each song. The problem is that artist popularity was missing in the dataset or was not present. So there were a process to calculate from each songs the popularity mean of each artist, and at the end there could be an overfitting risk, so an imputation value was necessary when the artist was unknown to, and this imputation was with the mean of artist population. Name length, in this case only shows the name of the song is a string, so the length is this variable, and similar to the other one, it shows a negative correlation, and it fit with a same pattern where songs with very long names tend to be unpopular. And the last one, the name language. There is some kind of pattern where English songs tend to be more popular, but this information wasn't in the original dataset, so it was calculated using a language detect task. And the language detection, well, for the language detection there are many options, many libraries, many options for being implemented, and the results were a high cardinality variable. As we can see, there is a difference of language detected from each library, but everyone, 46 for a categorical variable is not good. It's a high categorical variable, high cardinality variable, because they had many values. So an encoder was necessary, and at the end there were a comparison between combination of the detailed language libraries and encoder, and the result, as we can see in the image, the text blob in any case is the better for language detection. And well, checking the results manually, we can see that other libraries confuse Spanish with Italian, which is not the case of the text blob. It takes too much time. It was the longest to execute it, but it was the best prediction, the language prediction, and it results better with the target encoder. And well, at the end, this combination of text blob and target encoder was the chosen one. Once we finish the feature engineering, the next step is feature selection. In this case, we have two options, lasso and SFS. First, the Python implementation of SFS require a number of features to select. So an SFS task was executed using all features to detect any negative contribution of the model. As we can see in this image, there is no negative contribution to the model, but we can see that around the 13th feature there is an stall of the performance. So this is important because when we get the same, we get a similar result using lasso. We tested with different recommendation values for regularization, and the best one was a reduction of from 80 to 40 variables, and was excluding danceability, energy, liveness, and speechness. So having we have in the past the idea that around the 13 was the difference, but right now we have a number, a specific number. We have evidence to have a number, so we execute the SFS task again using the name that we get from lasso, and the result was a different subset of features. So we can consider like another version, and the variables were, well, were different. So to conclude, and cross-validation task was executed to see which subset was better. We can see with all feature with only SFS subset at Win Lasso. And well, they are very similar, but we saw an improvement with SFS, so it was the chosen one. And it's just to mention that the advantage here was the computational cost, because the performance is not a good advance here. And it is important to mention that none of the excluded features in any subset was generated in the feature engineering step. So we can trust that our variables or new variables are good ones. For the hyperparameter optimization, a model selection was needed. So 5 methods were contemplated, which are linear regression, retail regression, decision tree regression, extra tree regressor, and random forest regression. Unfortunately, there are not hyperparameters for the linear regression, at least not in the Python implementation, and there is only one for the retail regression method, but which is the regularization. But after some hyperparameter test, we only can get a very low improvement. You can see it in the screen is 0.00004 of improvement. So we cannot consider this. So we can see in our 5 methods we have like the linear methods, which are linear regression or rich regression, and the others are we consider like the 3 methods because they're based on 3. So we want to focus on the 3 methods. And the 3 methods, exhaustive exploration of the parameters was made, but it is really 2 hyperparameters, max deep and criterion. The max deep influence directly on the performance. When this parameter is none, the tree expands the node as much as possible, which is not the correct. It wasn't the best option. And when its value is numerical, the levels are limited, so the results to be the best option for all methods was limiting the expansion of the tree. We can see like setting the max deep in 11 in the decision tree and 15 for the extra tree and the random forest tree. There were not too much changes in the criterion, but we have two options: the Friedman's the this is the mean square errors, and the other option was the mean square error with Friedman's optimization. It results not different, so we get the measure the mean square error. In the case of the decision tree and the extra tree, they have an option to use the bagging regression. This is an ensemble of different splits of the data. Both cases, for both cases, this option was the best. It gets the best metrics. For the random forest, it wasn't necessary because it is already an ensemble. And at the end, using the best parameters for each method, we can see in the image that the random forest regression was the best option. It reduced the error are more, so we get it. We at the end we get this method. For conclusion, where the three tasks, the three steps were executed sequentially, and as we can see, we have this in this image we can see like we can base on what's the result in each step. The first one is just a linear regression with the original features, the non-string features. The next one is with the feature after the feature engineering. We can see that it reduced the error almost by half. So we have a great improvement here. The next one is the feature selection of the FFS was selected is almost the same. And at the end, the modeling with using the random forest and the best parameter for random forest. There is a reduction. It's not as big as the feature engineering, but there is a reduction. So having these results, we can conclude that for this dataset, a well-performed feature engineering task has a greater impact in the model performance than more sophisticated machine learning techniques. In this case, feature selection and hyperparameter optimization. As you can see, for the feature work, there's too much thing to do. This work was very limited with only one dataset. So the idea for the future is to see other dataset, test other dataset, and hopefully find the same pattern and to have a better comparison. Maybe use it like the every technique alone without any combination. So this is what we plan for future work. This is all for my part. Thank you so much. I hope you enjoyed the presentation.